So this chapter will discuss about how much the capacitor store the energy. Capacitor is store energy in an electric field. So if there are some charges stored in the capacitor in this way here, then there will be some electric field in this distance between the plus charge and minus charge. Because of this E field, there are the voltage potential. There will be studied in the electromagnetism in next semester. So there will be the voltage here. So if you insert the current, then the charge will increase. That means the voltage difference potential will be increased. So anyway, the stored power in the capacitor is, because we use the passive conversion here. This is V and this is I. Now the voltage will be the function of the current, but anyway, in some specific instant, the power stored in the capacitor is VI. So the energy stored in the capacitor is, because the energy is integral of the power for the time, so energy will be minus infinity time to the t as you want, p dt. There's the energy equation for calculating the capacitor. So, but the p is vi, so we adding, and we'll do that. So this is capacitor, this is a voltage, this is current. In this case, power is VI, and the energy stored in the capacitor will be integral the power t. Actually, is the tau. The tau is the function of the time. So because P is VI, so we end here. So there will be minus infinity to 2 VI tau. Then we know that the capacity equation is I will be C dt dV. So we insert this there. So there will be integral minus infinity to t. Then V I is C dt dV and d tau. Because C is constant, we assume that the C is constant. Then there will be C integral minus infinity to t v dt dv d tau. So because t is a time, so you can eliminate here and see v dv. Then that will be changed to the v t will be minus infinity, v is t. So they will be written more simply until v minus infinity vt vd v. So there will be c 1/2 v squared v minus infinity vt. So they will be written in here 1/2 c vt squared minus half c v minus infinity squared. What's the meaning of v minus infinity? That means the capacitor voltage when the time is minus infinity. That means we can guess that there will be 0. So they will be written half C V square. The unit of the energy is joule. So if you ask to answer, what is the energy stored in the capacitor? Then it will be half C V square. So if we have an example, this is 1.1 farad capacitance, and the voltage between the two polarity poles was 100 volts. Then how much energy is stored in this capacitor? That means W is 1/2 C V square. So 0.1 100 square. Then there will be excuse me, this is 500 joule. That's your energy stored in the capacitor. This is quite huge amount of energy. So there is a result. This is an example. Now there are capacitor. The capacitor is 10 millifarad. 10 millifarad is 0.01 farad, and voltage is stored here. So what is the energy? Capacitor energy, charge capacitor energy? It's simple. To solve the problems, we need to know these symbols. There's a switches. Switch is if it looks like here, then they will written here T was 2, for example. Then means first if when T is smaller than 2 seconds, then this switch is open. It's not connected. This is open circuit. And when T is larger than 2 seconds, then this is closed circuit. So what's the meaning of here? Because T is 0, then this is open. So that means when T is smaller than 0, then this circuit looks like 100 volts, and this is closed, and R and capacitor. And when T is less than 0, this circuit is open. This is open and capacitor. The question is, the time is 0 point. That means it is instant. Then there will be the 10 or 100 volts. Then what is the energy stored here? Because infinitely, if this voltage is 0, then can't follow here until this voltage will increase to the 100 volts. Then no current between here. No current means there are no voltage difference, voltage variation. So there is a steady state. So we can guess when the switch is open, there are no current flowing through this resistor. So the voltage of capacitor will be fixed at 100 volts. So energy in this state is 1/2, and C is 0.01 and 100 square. That is 50 joule. This is another example. It's quite simple, but it's fun story. It's very fun, but it's quite important. So problem is, this is a figure for the capacitor, and this is the voltage over here. This figure is the voltage. Then, to make a voltage waveform in this way, you capture your current and the power and energy. So we'll do that very simply. We will try to solve. So we need some space, so we will use some things. This is example 7.2 here. Okay. Then we will use because we need to find current and power and energy. So this is capacitor and this is CT, and we need to know CT first. So I want to define the equation of the voltage here. If with t is 0 when t is smaller than 0, then from 0 to second, then there will be increase is 100 over 2, and t there will be 50. And when t is larger than 2 and 3, then their value will be minus 50 t it's 200 here. And last, when t is less than 4, it's not, it's t, then there will be constant, it's 50. Oh, excuse me, and this is not 4, this is 3. Because at this point here. So based on here, we have the capacitor equation. What is that? It's I is C dt dV. Based on here, we can calculate the current ICT. At first, when t is smaller 0, there will be 0. When t is higher than 0, then we need to calculate based on here, because the current is the derivative of voltages, the capacitor, and to get that, we need to know about the capacitance over here. In problem, in textbook, you need to know about that. There will be your textbook page number is 266 and Farad is 5 millifarad. The capacitor is 5 millifarad. Then there will be 0.005 and DTD 50T. So there will be, how much is it? There will be 0.25. In the same way, when t is larger than 2 till 3, then there will be minus 0.5, 0.25. In the last, then t is larger than 3. So we can draw the current here. Oh, it's okay. Then it's 1, 1, 2, 3. And then we can do that. Here is this is 0, and from 0 to 2, their value is here, and their value is here, and there will be 0, right? So their value is 0.25, minus 0.25. That will be ICT. Then next is power. What is power? The power is VI. Basically 0 when t is a small 0. In the case of from 0 to second, then there will be 50 and 0.25. So there will be 12.5 t. In the same way, t is larger than second, and to 3, then we need to calculate here and here. So there will be 1 and 12.5 t, and that's right, minus 50. So, and last is 0. So we can draw the power, and the figure looks like here. This is 1 and 2 and 3. Because second 2, the value will be 25. Doing this watt, and the link is here, and here we will use here minus 25, and here in this way. So power is looks like that. It's 0 and go up and go up and here. So this area means current is positive, the charging area. And this area, the power is negative, that means discharge. The last, we'll do the energy here. W is integral P dt. So there will be 0 for t is larger than 0. The next is, which is we integral 0 to t 12.5 tau d tau. Because of that, 6.25 t square, and there will be double 0, but in the case it's 0, so there will be answer. And in the case of here is this will be 0 t second. Here in the third case there will be is second to t, then and power is here to 5 t minus 50 t tau and plus v, and so excuse me, this is not v, this w, t will be 2. So from here you can calculate the t will be 6.25. But actually, because we have to do here 2.5 t square minus 50t, and this is 0.t and here from the 2 and plus w2. And last thing is there will be 6.25 t minus 50t and so on. We calculate here, so we can draw the energy here. It's very simple. When power is 0, the energy direction is 0. Power is increased here, that means energy increase is in this way here, because this is the variation, and this is negative, that means discharge, so the energy will reduce in this way here. Then there are no current, no power, so there will be power. So that value is 25. That's way. This is stored energy here in this area. This is discharge area. This is a holding area. In the case of resistor circuit, for example, this is 10 volts, and there are the resistor here and the resistor here. Then it is 20 ohms. It's 20 ohms. So in viewpoint of this source, this circuit is same with 10 volts, and this is 10 ohm. Why? This parallel connected resistor is equivalent, only Q will be 1/20, so there will be 10 ohm. So in the case of capacitor, there are many capacitor combination. It could be connected parallel or series. So this chapter we will discuss about the equivalent capacitance when capacitor is connected in parallel, or when the capacitor is connected in series. will discuss about this when we have this, the parallel connected capacitor. And here, then as you see here, what is the same with these excuse me, this and this. The viewpoint of this second, that when in the voltage of here and this current and voltage of here, this current, that this voltage V1 and V2, and V1 is equal to V2, and this is I1 and I2, and I1 equal to I2. Then you can say this circuit and this circuit can be equivalent. So to do it here, so to do this, when we wanted to say the equivalent things of this and this, then we need to know about this current or this current and this voltage. The voltage will be same. So you need to think about here when define this current source. I don't know how much is it. It is I, and we have N capacitor here, N capacitor here. Then, based on the KCL, because this is a one node, I is the same with I1. This is I1. This contains I2 plus I2 IN. And in the viewpoint of one capacitor, we can say, because of capacitor equation, I1 is C1 dt dV1, and I2 in the same way, C2 dt dV2. The same way, IN will be Cn dt dVn. But in this case, because capacitor is connected in parallel, so this V1, this V2, and this V is all the same. V1 equal to V2 equal to V3 equal to V4, all V. So we can replace these equations here. Then I can be rewritten C1 dt dV plus C2 dt dV plus Cn dt dV, because dt and dV dt is a common, so it can be rewritten here. C1 plus C2 plus Cn dt dV is I current. How about this? In this case, we can say This is current I, and this is V. So I is Cp dt dV. So if two cases is the same, that means Cp is equal to this. Therefore, parallel connected capacitance is the same with all capacitance in this manner. Then how about the series capacitor? When capacitor is connected in series way, and we can get equivalent capacitance. We can do this for the same way. This is series capacitance here. So when you say this is the same with each other, then this is connect capacitance, and this capacitance is the same when the current over here and current over here and all voltage between here and here and here same, then you can say this capacitance is the same. This is the same. So we will redraw this circle a little bit. This is the same way. This is V, and capacitor connected in this manner. And this is the same with one capacitor. So we'll define this here. This is V1, V2, V3, Vn, and current is common. We say this is current I. Then because of the KVL, we can say V is the same with V1 plus V2 plus Vn. Then what is the Vn, the Vi, or Vn? That is simple, because capacitor equation I is C dt dV. From here, V is 1 over C into rho T0 T I d tau, and plus V when T is the same with T0. That is a V. So based on here, you can rewrite. Okay, we need to move there. We need to move. Yeah. Okay. Therefore, based on equations, we write V1 is 1 over C1 T0 T I d tau plus V1 T0. because I is common, because all current through the capacitor V1, Vn, V2, V3, and Vn is common I. So we define this as I. And plus V2 is 1 over C2 integral T0T I tau plus V2T 0. The same way, 1 over Cm integral T0T I d tau plus Vn T 0. So as you see, this term and this term is common for all capacitor because current is common. So we can rewrite this V is based on here 1 over C1 plus 1 over C2 1 over Cn integral T0T I d tau plus sigma n equal to n Vn T0. So we can rewrite here is sigma n equals to n Cn1 this n into T0T I d tau plus T0. So to compare it here, this is Cs, then this is V, this is I. Based on here, we can write V is equal to 1 over Cs integral T0 to T I d tau plus V T0. Actually, this is the same with V T0. Therefore, that term is same with that term. So what is that? Therefore, 1 over Cs is equal to here. So where is that? Stated correctly, Cs is the same with inverse. This is like that 1 over C1 plus 1 over C2 plus 1 over Cn and inverse. So this is the same with when the capacitor is connected in series, then this is similar equation when the resistor is connected in the parallel. And when capacitor is connected in parallel, this is a similar form when the resistor is connected in series. So this is example of here. Example of this problem, find the equivalent capacitor is it's a very simple problem that we will try to do to solve here. Okay. First, this is a very simple, but you need to know we make a equivalent capacitance here. Then the condition over here is all capacitance is 2 millifarad. Then but V1 of the initial voltage over here is 10 volt. Now this is a 20 volt. So actually it's not important in the viewpoint over here because we need only to know about the capacitance. As you see, this capacitance can be redrawn is Vs and capacitor here, capacitor here, and capacitor here. It looks like here. Then at first we can make these capacitance. Actually, this is C1, C2, C3. Then we can make equivalent to one capacitor here. Because this is connected in parallel, therefore there is a C2 plus C3. And here C1. Then this is the same way on capacitor. This is series connected in C1 and C2 plus C. This is connected in the series CEQ. There, because this is connected in series, there's a 1 over C1 plus 1 over C2 plus C3 and inverse. So there will be C1 and C2 plus C3 and C1 plus C2 plus C3 inverse values. So there will be C1 plus C2 plus C3 and C1 C2 plus C3. So that value is 2 millifarad. So 0 is 0.006 and 0.002 and 0.004. So that value will be 4 here. So our EQ will be millifarad. Actually, this problem, this voltage value is not important here because we just want to know the equivalent capacitor of this circuit. So it's very simple. When you calculate the resistance when the resistor is connected in series, is very serious problem. Then we will do this in another example here. Next is the exercise or problem. Okay. We need to find equivalent capacitor here. So it's a very simple way. And as I always say, when you have the circuit, I recommend you draw by yourself to understand what is this circuit. I will redraw the circuit here. At first, there are 6 millifarad, and there's a branch here. So we have 9 and 2 series connected capacitor here. It looks like that, and there's the here. So this is CEQ. Then this is 6 millifarad. It's 9 millifarad, and this is 12 millifarad, and 4 millifarad. Okay, then what should we do? We make equivalent capacitance here. Where is that? Because capacitor is connected, then this is the same with the sum of these capacitance. So this capacitance is 12, 4, 16 millifarad. Then next, these capacitance, it looks like the series connect. I'm sorry. Always always my mistake. When the resistor is connected, then we can add here. But this is long. In the case of capacitance, when capacitor is connected in series, then there is 1/12, 1/4 inverse. So there will be 12/4, 3 millifarad. It's long. You don't confuse of this case. And that means there are 9 millifarad and 3 millifarad capacitor. So this is parallel connected in the case of here. So this circuit is same way here. Is 9 plus 3 is 12 millifarad. Then we can redraw this circuit this is 6 millifarad and this is 12 millifarad. Then 6 millifarad capacitor and 12 millifarad capacitor is connected in series. So equivalent over here is 1/6, 1/12 inverse. That will be 12, 3 inverse will be 4. Unit is millifarad. So this is CEQ. Don't confuse of that. Don't confuse of them when the capacitor is connected in series, and when R case, R is connected here, R1, R2, and this is same way. The Q is R1 plus R2. When resistor is connected in parallel way, R1, R2, then RQ is 1/R2, 1/R1, R2, and inverse. In the case of capacitance, when capacitor is connected in series, C1, C2, then CEQ is same with 1/C1, 1/C2 inverse. When capacitor is connected in parallel way, so C1, C2, and CEQ is C1 plus C2. Do not confuse of these things. And another thing is we will discuss about the inductor. Inductor is on the passive element in the electric circuit. There is consists of the core and the coil. So inductor stored the energy in the magnetic field. So inductance is a measure of ability of a device to store energy in the form of the magnetic field. So when you see some kind of some iron here, and there are many coils in this way here, then you can say that will be inductor. You can think like that. You remember when you were the elementary student, then you have a this is nail here, and you make winding up in the coil like in this manner. And you insert here is a battery. Is it plus minus battery in this manner? Then you put on here, you place the glass, and then you spread the iron powder. Then iron you place in this way. You remember that. And then it looks like magnetics. It looks like the same phenomenon of magnet. We call this is a solenoid. We will learn about here later, maybe yours the semester. Then the reason to place this iron powder in this way is the magnet field. Magnet field. It means magnet field is generated when you have the permanent magnet, or in the same reason that you can have a magnet field when you make a current here. When the conductor, the flow of the current, then around of the conductor there are the magnet field. So to make a magnet field, that means there are some energies in this coil in the area. So we call this structure is inductor. Inductor means a kind of the energy storage device in the manner of the magnetic field. So inductor consists of the core. This is in the case the nail is a core. The reason we have the core is magnetic field can be generated depending on the material. In the iron and ferrite, such like the core, we can use the core. Then there are many. The magnetic field can be generated well. But in the air or water and the wood, magnetic field is not generated well. So when you want to store the magnetic field, then you should use the core, such like the iron or ferrite in this way. So inductor need the core and the wrap with the coil in this way here. So the symbol of inductor is in here. Then you define this is L, is inductance, and this is the V in current. We use passive convention. Then the inductance in the geometry, inductance is calculated this way here. So inductance L is length over here, and mu is permeability. In Korean is 투자율. There. And this permeability is not only the core but also in the air in this area, because the magnetic field generated in this way here. So half of them is going to the core and another half of them is going to the air. So when you get the permeability that we need of the here, and N is ton number, how many tons is wrapped the core by the coil, and A is a cross section over here, and L is a length in this. So inductance can be written in here. Actually, this inductance is not important. This equation is not important in the circuit theory, because we don't care about how you make this inductance. This will be deal with later in the electromagnetism, or the later is the electric energy circuit. Then you can calculate inductance, and you can assume that inductance, or you can design the inductor as you want to make as you want specified the inductance. But in this circuit theory, we just only to know about the lumped parameters of inductance, and the equation of that is V of inductor is L dt di, you know. So you need to figure out the capacitor case. So in this case, the inductor, the V in the inductor equation is V equal L dt di. You should use passive convention here. In the same way, this integral form is I will be 1 of L integral minus infinity to T V d tau. You need to check it. In the case of capacitor, this is V and C and I. Then what is the capacitor equation? I is C dt dV. So V was 1 over C integral minus infinity T I d tau. So you know L V L and I and V I and I V I V V I. This is a dual. This is a dual. Don't confuse about that. In this equation, you can know about that. The capacitor store the electric field. The electric field is proportional to the voltage difference in voltage potential. This is voltage. But the inductor store the energy in the magnetic field. The magnetic field is proportional to the current. So here energy is stored is by magnetic field and by electric field. So this is proportional to the voltage, but this is proportional to the current. So the voltage over here is current over here. So in the capacitor, the voltage is continuous. But in this case, current is continuous. Because inductor case, inductor is stored in the current. You remember that the energy of stored in the capacitor is 1 over C V square. But in the case of inductor, maybe you can guess there will be 1 over 2 L current square, because this is dual. We call this is duality. So we will discuss about later. So the current in the inductance cannot change instantaneously. That means the current in the inductance is continuous. So this is the inductor equation is V is L dt di. Therefore, the I is 1 over L is integral of V. So we rewrite here. This is the minus infinity to t0 and t0 to t. This is specific time. So we'll define this as I t0. They will call this the initial condition of the current. So this is example over here. When you say this is inductance here, and this is voltage source. So based on here, we can get the relationship between the voltage and current in the inductor. That will be V is L dt di. So we can check it about that. So for example, we have this waveform of current of the inductor here. Then we can rewrite this is I will be 0 when t is smaller than 0. But when t is from 0 to t1, there will be t1 t. And then t is higher than t, there will be 10. So based on here, we can get the V gets in here. V is the derivative of I. So we can rewrite here. There will be L dt d0 will be 0 for t is smaller, and then L dt d and t1t will be t1L and 10 when t is from 0 to t1, and L dtd 10 will be 0 when after t1. So there will be, this is the 0 values, and that is here. This is value is t1 L and 10, and this is 0 values here. So the current inductance cannot change instantaneously. Why? Because the energy in the conductor is stored in the current. When you say the current is the varying in the stepwise, that means energy stored in the inductor is step changes. It is impossible. But the voltage can be stepwise because the voltage kind of the derivative of the current. That means a ratio of the stored energy in the inductor is the voltage. So voltage can be changed in the stepwise in the inductor. This is the dual in the capacitance. So we have some example here. Find the voltage across the inductor when L is 0.1. And so current in this way here. Then we know the inductor equation. What is that? When you say this is inductor, then you can say the V and this current I. The relationship between the current and voltage. Then what is that? V is L dt di. So we know that with 0.1 and dTd, the current is this equation. So 20t exponential here. So it's very simple. You can do that. 0.1 and 20e here plus 20t and minus 2 in here. So there will be 0.21 20e t minus 40 t e. So we can rewrite 2e t minus 4t e minus. So we can make a simple 1 minus 2t. You know this is volt. So what's the meaning over here? When you draw this equation is the current, it looks like in this manner. And what's the meaning over here? This area, the current is increased. That means the energy is stored in the inductance. That means the voltage of inductor is positive values, then current is increase. So this area, the voltage is positive values. And after that, the current is decreased. That means this voltage is negative values. So current is decrease. There's a negative value over here. This is another example. Determine the inductance over here. When this is voltage is V and current is I and L is here. The waveform of this is 3 and this increase in this way here. So we can check it. V is 3 when t is from 2 to 6. And here now I is, this is 4 millisecond. So ratio of that here is 0.004. The amount of the ratio is minus 2 to 1, so 3. And t minus I don't know, but we need to know that about here. Is t plus a. Then when t is 6, and it's actually not 6. This is a millisecond here, so this is not 6. 0.006. So 0.004, 3, 0.006 plus a should be 1, because in the 6 this is 1. So 3, 2, 3 plus a will be 1. So this is 9. So a is 1 minus 9 over 2. So there will be net values. So it will be 0.0043t minus 7/2. Okay. Then anyway, actually this is not important here. Why? Because of here is v is L dTdI. Then what is v? V is here is 30. Is L, what is the dTdI? dTdI is here 0.0043 t minus 7/2. So there will be L 0.0043. This is 30. So L will be 3.004 10, then 0.04 unit over here is Henry, so you can rewrite 40 millihenry. So we can write here is in this way. So here you need to know the case of L. In the case of L is this is important here. So we summarize here. This is R, and this is capacitor, and this is inductor. Then there will be voltage here, and this is current. Also the voltage here, this is current. This is a voltage here, and this is current. In the case of the R, then V is RI, or I is 1/RV. In the case of the capacitor, is I is C dTdV. And in the case of inductor, the V is L dTdI. And otherwise, the V is 1/C into I dt. This is the I is 1/L into L V dt. So there are three very element component of circuit theory is R, L, and C, and their relationship between the voltage and capacitor in the each R, C, L, C is looks like here. You should do not confuse over here. And other thing is the same. You can use KCL, KVL, voltage source transformation, and source transformation, and Thevenin equivalent, and mesh equation, node equation. Everything is same, but different thing is that these equations. Unfortunately, if we have circuit has a capacitor or inductor, then the relationship between current and voltage looks like the derivative equations. So when you make a mesh equation or the node equation, then the equation will be derivative equations. So you should solve the differential equation. So that is the only difference in between the only resistive circuit and the inductor or capacitor included circuit.